This video is sponsored by PCBWay. Welcome everyone. In this video I'm going to show you some motion control related stuff again. In some of my older videos I showed you how to control a DC motor using PID, and I'm going to do something similar here but using different kinds of motors. And I found these motors on eBay or AliExpress quite often, but I haven't found too many applications based on these motors, and I would like to create a video where I show you the basics and show you solid basis which you can use to further develop these things into something useful stuff. And first let's talk about these motors, because they come in different sizes and shapes. So let's first look at this. So this can be often found as N20 geared DC motor, and yeah, as I said, they come in different sizes and shapes. This one I have written on it before I forget it. It's a 12-volt version. You can find a 6-volt version as well and other supply voltages, and this specific one is with 200 RPM version. And usually on the AliExpress pages you can find different tables where you can see the voltage, the current, the torque and all these things, and they often state the gear ratio next to the no load RPM value. So you have to look that up, but when I show you the code which I implemented for the Arduino, I will explain these in more details. So typically they come in this kind of let's say package. So here we have the gearbox, different gear ratios, and then we have an M4 threaded rod or lead screw with a flat end, which you can use to put this in a nice bearing or something which supports this thing and allows it to rotate. And then we have the magnetic encoder here, and probably you can see the three spots at the edge of the circle, and those are three magnets. So these encoders are 3 PPR encoders, or pulses per revolution, and then we have 6 cables. So starting at the black, this is the negative supply of the motor, and then the red is the positive supply of the motor, and then the yellow is the positive supply for the encoder, which can be between 3.3 to 12 volts. And then the green is the negative counterpart of the encoder supply, so that's the ground. And then we have the two wires which are left here. Blue is the encoder A, and white obviously will be the encoder B. So these two, white and blue, go to your Arduino, and then these two are the supply pins. They can also be supplied by the Arduino because it doesn't take too much current, and then these will go to a motor driver. And in this video I will show you the motor driver, which is the TB6612. It's a 2-channel PWM driver, so that will be used with an Arduino and some other hardware to drive this motor. So this is the most typical package: motor, gearbox and a straight shaft. But sometimes these motors are in a different arrangement. So you can see that the shaft is right next to the motor, but same arrangement. You have the magnetic encoder, the Hall sensors, the 6 wires, gearbox and another shaft. And then this is a smaller version, and I already printed a carriage for this. So you can see where this goes. You can create something like a linear carriage and use it for positioning on a one-dimensional axis. And of course you can put several on top of each other, so you can have 2-axis or 3-axis table. And yes, wire is missing here because it broke off. So I have to notice here that these wires are really sensitive for bending. So try to avoid bending these wires because they break, and it's very hard to get them back where they belong, because the magnet is blocking the view or the access for the tip of the soldering iron. So yeah, just to show you as an example, this is now cold, it's not really connected. It's quite hard to get your soldering iron there, and then another challenge is to get the wire inside where it belongs. And it's not easy, I haven't tried it, but I guess it's not easy to pry off this magnetic wheel. So yeah, once you lose those wires, then most likely you have to throw away the motor. And then just another, this is my latest build. So 10 centimeter long shaft, and then I have two 4mm diameter steel shafts as a supporting part. And then here I have the crosshead, and then the 6 wires are here, and we have a limit switch here, so this can do homing. And then here is just a hole to support the threaded rod. And you can see that also we have this guy here. I'm not going to lift it too much because I have all the wires put together here, but I have a shorter motor here, similar to this, in a similar arrangement. And then you can see that this thing is 3D printed. I will share all these designs on my website, so you can pick it for the shorter, I think 55 or 50mm long shaft, and this is for the 100mm long shaft. Freely accessible on my website, and I will put some instructions and some pictures how to put these things together. But then this brings us to the sponsor of this video, PCBWay, because they can also help you to, for example, print these kind of things if you don't have a 3D printer at home. So head over to their website and find their 3D printing services, and for example you can upload these files, or you can upload more sophisticated designs to their website, and they can print beautifully using different materials, anything starting from very basic materials to even metals. And if that would not be enough and you would like to do this using CNC services, for example, then they also can help you with that. So if you want to have these parts machined out of a metal, then just head over to their website, find their CNC service related page, and then try to order as you wish. So I hope you will like PCBWay services and you will use them. And now let's talk a bit more about this system. So the system here, I try to center it more, it consists of this motor. Yeah, so for example, this guy here, inside a linear carriage, we have a limit switch, so we can do a homing here. And then what we have here is an Arduino Nano, for the sake of simplicity. I put a display here just to be able to see a set target distance. So I will take a closer video of this display and you will see what we are doing. And then a rotary encoder just to control this thing. And then we have the 2-channel driver for the DC motor, and then just the power supply connector for 12-volt power supply, which will only power the motor driver. And then for this I will just use a USB cable. So then, as you might suspect, we have the encoders which require a pull-up resistor each pin. So I'm not only using the internal pull-ups here for the Arduino, but I'm also using external resistors. So just to be safe, I'm using some extra stuff here. And again, go to my website, link is in the description, and you will find all the wiring diagrams for this, some extra pictures as well, so you will see a lot of resources. And obviously you will find the source code on my Patreon website as well. So what I will do in this setup, I will start this thing, and I wrote the code, which I will tell line by line later, in a way that when I power up everything and the Arduino boots, after booting, the carriage will go home and then it will park. And after that, I can set a target distance and then the carriage will travel there. And the reason why I have this digital caliper here is because I want to show you how precise this thing is. It's not very precise, but it does the job, and you will see how it does the job. So let me wire up everything, and then we start with the fun part. So now I have everything ready. and hopefully you will see the display clearly enough. So here I have the laboratory power supply, 12 volts, and I haven't turned it on yet, but I will turn it on now. And then we have the Arduino, so let's just connect this thing. So now it does the homing, so this is going backwards. And it reached the switch, then it switched position or target direction. So then it started to move away from the gearbox towards this end of the carriage, and then it moved until the switch was released. And there is nothing extraordinary behind this part of the code. You will see it, it's very simple, just the switching directions of the motor and running the motor with a relatively low PWM value, so it goes slowly, but there is no PID for this part. And then hopefully on the other display you can see the display itself. I will try to focus it, so now it should be better. So on the top we have the target position, which I just randomly programmed as 2.3 millimeters, and then the position on the bottom is just the calculated position based on the number of pulses received from the encoder at the end of the moving process. So now what I'm going to do is that I turn on the digital caliper, so now we are at 0, and I measure a small gap between the end of the gearbox here and the beginning of this crosshead. And why I do that is because I want to know the distance, which is my reference distance. And then that is now, hopefully you see it, 4 millimeters. So I zero this out right now. So this is done. I leave it here. And then I just press the button, so then this thing, should travel 2.3 millimeters. So according to the display first, you can see that the bottom went to 2.3, and that is based on the number of pulses received from the encoder. And when I show you the code, I will explain you how to calculate this thing based on the gear ratio, the thread pitch, and the number of pulses per revolution from the encoder. But now I have to measure that gap. So now we are at 0. I try to show it to the display, and then I try to measure it properly. So 2.24, and that is like 60 micrometer far away from the position reported here. And then there can be several reasons behind that. Maybe it's not precisely moving, and also the mechanics is a bit wobbly, and also, which can be an issue, is that measuring between these two parts is not the most precise thing ever, because these are not very parallel. So I can introduce the error using the caliper as well. But I would say it's close enough. So if you would, neglect the last digit, then I would say it's okay. So now I set up some random position. So let's say 7.7 millimeters. So I just press the button, and then it moves. So we wait a little bit. And then again, on the bottom of the display, you see 7.7. So that's the reported distance based on the number of pulses. But let's measure the gap again. And we zeroed the position where we had to zero, so at the original gap distance. So I'm just continuing that measurement. Look at there, so 7.7. So it's not too bad. And let's move one more bigger step forward. I don't know, 13.3. And let's see what happens. So now you can see that it ran over a little bit, so 50 micrometers more. But let's see what the caliper says. and the caliper says kind of the same as the encoder. Sorry for the stupid reflections. Now you could see it, so it's close enough. And then just to show you that this thing can have, for example, backlash, because there is no backlash, how to say, there's no backlash compensation here. So now I turn directions, so I go for, let's go back to the 7 millimeter position. There should be probably a bit more discrepancy. And this is a funny thing that you see here, or hear it, that the motor is a bit struggling because the error value in the PID is a little bit different than 0. So the code constantly trying to reach 0 error value, but that doesn't work. And still you can hear this annoying noise. I will get rid of this soon. And that is because the driver is still receiving a small value as the PWM value. So then it tries to move the motor, but the amount of current run through the motor based on this very low PWM value is not enough to turn the motor. So that's why you hear this noise, and it's not good for the motor, but now we do this for science. And 7.10, that also suggests that the motor should still go, and that's the same suggestion as the noise. So let's go somewhere. And now we should be at 10.05, so let's see. If I could measure a bit more better. So 10.22, and that is because I suspect that we switched the directions a few times and the backlash is not compensated. Let's measure it just once more. Yeah. Whatever I do, it stays like this. So it's not something that I introduced. So it's 10.2 something. So yeah, it is what it is. So let's go back to some small number again, 3.4. And let's see what we measure. So the motor suffers again because of this, probably not the perfect PID parameters, I can imagine. And it's, just measure it twice, 3.51. So 3.4 versus 3.51. So it's, let's say, close enough. It's not too bad. So now I reset the Arduino, so it's going to go home now. And it's at home. So this is what I wanted to demonstrate to you. So if you want to use this motor or linear guide to position your whatever which is your object on the crosshead with, let's say, 0.1 or 0.2 millimeters precision, then this thing can do it. And I'm pretty much convinced that someone else out there could improve my code, especially the PWM part. So this could be used even better than I could use here. So I really encourage you to try my code and try to play around with all the parameters and everything, because I believe that you can improve this thing. But I just want to publish this as a jumping board, because these motors are actually quite useful and they are relatively cheap. And in many applications they can be kind of better candidates than stepper motors. And now we will go to my computer and I will show you the coding part, and I will also talk about the calculations which can be used to convert the number of pulses into millimeters, or if you want to feed the target distance in millimeters, how that can be translated into number of pulses, so how the motor can find its target. So let's go to my computer and then I will show you the code line by line. Okay, so we are looking at the Arduino code now, and I'm going to guide you through this very fast. So this is copy-paste. I've been recycling this code for quite a long time. So this is how I use the OLED display. You can see the exact same lines in some of my older codes as well, because it works. Why change it? So this is just the SSD 1306 ASCII wire library and the normal ASCII wire library. So these two for the OLED display. And then just the address, which you can see on the back side of the OLED display, and then some other variables. And of course, you have to create an instance here. So whenever you try to call a function from the OLED's library, then you refer to OLED, for example, OLED.print and so on. But this, really is just copy-paste, and then you will see how to use it. And then here we have the pins for the rotary encoder, 3 pins. 2 are related to the rotation, and then 1 is to the button. And one thing that you have to notice, which I also wrote here, highlighted it, that here we use the number 2 pin of the Arduino Nano, which is an interrupt pin, and that is important because whenever there is a change on that pin, that will be captured by the Arduino Nano, and then it will run the interrupt function, and then we will see, or the code will see, what it has to do. And then DT pin is just the random digital pin, and another random digital pin is the SW. And then these 2 variables, you will see it in the interrupt function, are related to a dirty but quite comfortable implementation. I keep track of the time elapsed between 2 clicks on the rotary encoder, and if they are coming in faster than a certain threshold value, then I increase the increment factor, so there will be a larger step size. And this is good because if you turn the rotary encoder fast, then you will increase the value of your variable with the larger step size. And if you turn it slowly, then you just increase or decrease your variable with basically 1 step size or whatever step size you set up. And then, we have to keep track of these variables and their change, because we will determine the direction by checking these variables against each other. And based on that, we will be able to determine the direction, as I said, and we will know whether we should increase or decrease the value of the variable that we manipulate with the rotary encoder. And then this is kind of a debouncing. You will see it, how it works. So here I just write that button debouncing. It's again a dirty but comfortable implementation. Limit switch, I just put it on the pin number 11. I'm not using the SPI in this project, so I can use the pin 11. Otherwise, I would not use it if I would use SPI. And since the motions or the movement of the carriage is slow, I can afford pulling the output of the pin or output of the switch because the code can react in time. Then we have these 2 encoders or encoder pins from the motor, and the number 3 is again an interrupt. I just write it here. And then the other is just a normal input pin. And then we have a volatile long variable which stores the motor position. So this is the number of clicks for the encoder. And then basically this will be converted into this or vice versa. Target mm, so this is the target in millimeters, and now this is my, let's say, startup value, 2.3 millimeters. Then go to home, again, whether we allow homing or not, it doesn't need much more explanation. Switch motors, so this will be used as a flag, whether we should switch the PWM driver, and by switching, I mean setting up the direction. So controlling the value of the A1 and A2 pin, or B1, B2, and then controlling the status of the standby pin. So this will basically end up in 3 outcomes: clockwise rotation, counterclockwise rotation, or stop or break. They are the same. I missed the bracket here. And then update value, update the display or not. And I made it volatile because I update this in the, or change the variable inside the interrupt of the rotary encoder switch, so, or a rotary encoder. So yeah, just for the sake of safety. And then, as I said, there's a standby pin on the controller. So this is connected to pin number 9. And once again, visit my website, link is in the description, because I put the wiring there so you can see it. But if you still, I just tell you this as an advice, you can always track back the wiring in my codes and in any other person's Arduino code by just reading, really, because it says that you have a standby pin, and then that is connected to terminal or pin number 9 on your microcontroller. And again, you see A1 pin, which goes to the A1 pin on the driver, is connected to the Arduino pin 8. So it's very obvious. You don't need actually to use the schematics, because you have the schematics here written as a text. It's very obvious. So yeah, standby pin, A1, A2, and PWM. So this is what you need for controlling one motor. If you would need the other side, then you would need another PWM, and then you have B in 2 and B in 1, but now we don't mix it there. And then these are my more or less guesstimated parameters for the 3 terms in the PID. And then you can see here some earlier parameters, because I've been playing around with other motors and stuff like that, so I kept them there. And then control signal, yeah, that will be the control signal for the PWM. And then these are just the PID related stuff. I won't list them what is what, because the name of the variable pretty much tells what they do. And basically that's all about the all the variables. So just read the code. Then we arrive in the setup. So this part of the code runs when you power up the Arduino. So I've been debugging this through the serial port. So we have a serial connection, and I will also show you here some cool stuff. The setup, which you saw a few minutes ago on my workshop bench, is now next to me and wired up, but I want to show you something very cool. So that's why I still need the serial. And then also we need the I2C, and then I define these pins as input pull up. They are actually already pulled up based on the module circuit, because that module contains the components to pull up the pins, but I want to be sure twice. Therefore I use the pull up resistors inside the Arduino for the input pins. And this is the first, this is pin number 2, the CLK pin on the rotary encoder. This will be used as the trigger for running the rotary encoder function. And then as we need the status or state of these 2 pins, we read them here now and put them in the CLK previous and DT previous variables. And then we have the limit switch pin, again input pull up. And yeah, reminder, if you pull a pin up, I know it sounds very suggestive and it makes sense, but it's not always obvious for people. If you apply the input pull up on the pin, it will be pulled up. So whenever you do a digital read on those pins, which have been defined like this, they will report number 1 as the state. So when you put a switch on these pins, you have to pull them to the ground. So when you short the pin of the switch, in this case the limit switch, one pin goes to the to the pin on your Arduino, and the other should be connected to the ground, just so you see. And then also we have the encoder pins from the motor. And as I said, I added some extra resistors just to be safe, 1 kilo ohm resistors or something like that. I don't remember the exact value, either 1 or 4.7. I will write it on the video. And then all the other pins, standby, A1, A2, which are the direction pins, and then PWM, they are all output pins. And then I also set them up and pull everything to low, because I want to block the motor in the beginning. And then this belongs to the encoder on the motor, so I need another interrupt to capture the status change on the motor encoder, so I use the encoder pin 1, and that will fire the encoder count function. Again, copy-paste this part. This will just start up the OLED, as you see it, begin. And then here I just set up a font, clear the display, and I print some welcome message. Now it's PID controller, and then I let it be on the display for 1 second. You can change this, and then clear the whole display so it becomes blank, and then I print the static parts on the display. After that, I let the motor to go home, and I perform the homing. This is a blocking function, so the code enters into this function. You will see how it works, and then it stays there until it is finished. And I put this here for us, first of all for myself, because I always tend to forget this thing, and it's easy to look it up if it's in the code, but also for you who is reading the code, that this is the code for the pin states for the TB6612 driver. So if you want the motor to run counterclockwise, then this has to be the input pin. Input pin 1 is low, input pin 2 is high. And then you flip these two if you want to go in the opposite direction, obvious. And if you want to stop, everything is low, as I did right here. Then we are in the loop. And then, we are polling the rotary button. If we have the PID enabled, then we drive the motor based on the calculated PID parameters, and we print 3 variables: the target position, the actual position of the motor, and the control signal. And this is basically the cool stuff that I want to show you soon, so stay tuned. And then we also update the target position, but this function is only accessed by the code whenever it is allowed to be accessed by the encoder. So then let's start with the homing, because that shows up here first, so that will be the first thing that the Arduino does when we power it up. So this became true because we put it there. So we are allowed to enter this part, and the first part we encounter is the while part here. And as I said earlier, this is defined with input pull up, so its default state is 1. So when you don't press the limit switch, the corresponding input pin will read 1 with this digital read. So basically this code line means that, it's written here, until we don't press the switch, do whatever is defined here between the braces or brackets. So this we do just once, and how we do it once, that if the switch motors is true, which is true in the beginning, then we enter this if condition, and we just set up the direction of the pin and allow the motor to move by setting the standby pin to high. And then we put this into false, so in the next iteration of the while loop, we will not enter this part anymore because we don't need to enter. And then we just wait a little bit here, and then we update the value of the PWM pin to 100, so roughly a little bit less than half speed. And I put 120 here because it can be higher. So then, until we don't press the switch, we just iterate this part over and over. So we run the motor towards the limit switch. And once the limit switch is hit, then this is false because the limit switch pin will give you 0. So then as soon as we step out, we set the PWM value to 0 and we shut down the motor. And then I allow the code to switch the motors again, and we flip a direction. So we enter here, and what this line means is that as long or until the switch is not released, so this is wrong here. So while we haven't released the switch, possibly not the best grammar here that I used, but you understand. So until the limit switch is pressed, so that means that it is shorted to the ground, so it reads 0, we stay in this function. And then we flip the direction, so we run away from the limit switch, and then we do it a bit slower, so we slowly release the switch. And then when the switch is released, we are shutting down the motor, setting the PWM value to 0, and then just to be sure, we allow the motors to switch directions again. And then this is false, so we don't want to do homing anymore, and I zero out the motor position to 0. So this will be our 0 position. So the encoders on the motor, or encoder on the motor, will start counting from this position. And this was the position also corresponding to the small gap which I was measuring with the caliper, that roughly 4 millimeters or something like that. So this is the homing. It's quite simple. It's just a lot of lines, but yeah, probably someone who knows coding better than me, those people are not too hard to find anyway, they can improve this code probably half of the line, or half of the number of lines or something. So feel free to improve my code. I'm very happy to accept any kind of constructive critiques and comments. So go on, please. So then homing is done. So we can move the encoder, the rotary encoder, to set up a target position. So let me go there first, because I want to show you the adaptive stuff. So when the rotary encoder is moved, then that triggers this function, and then we read the CRK pin. And then we just do some comparison in order to see what's up with the motor, with the rotary encoder, sorry. And now, if this state is true, then we enter this part. And here comes the adaptive part. So what we do here is we read, basically the Arduino looks at the clock right now when it reaches this part of the code, and then it checks that if the time now minus the time I looked at it the last time, says the Arduino, is less than 50 milliseconds, because here we use the millis, that means that the time difference between 2 clicks was less than 50 milliseconds. Then we did a fast turn on the knob of the rotary encoder. So I set the increment factor to 1, and that is 1 millimeters here. Otherwise, if the time between 2 clicks was more than 50 milliseconds, then I set the increment factor to a small value, which is here 50 micrometers. And then I reset the timer. So again, the timer, when the code returns to this part, will measure the time difference between this line and again this line. And then based on this outcome, so if the DT and the CRK now pins are equal or not, based on that we either increase or decrease the target distance. So that's quite yeah, straightforward. And then I let the display to print the new values, and then I just yeah, update the previous value of the CRK, and that's all. And then I just want to show you the simple parts, let's say, before entering the more difficult parts. So yeah, here it's very obvious. So there is nothing extraordinary here. This is the encoder of the motor. Maybe I should make it obvious. So then the encoder is fired, and then we check the status of the other pin. And why we need to check it like this is because we have two square waves, and they are shifted against each other with a certain, let's call it, phase. And then if they are shifted in a way that the encoder pin is 0, then the motor runs in the positive direction in our coordinate system, let's say. Otherwise, it runs in the other direction. So it means that, let's say, the pulse on pin A is ahead of the pin B, or the pulse on the pin A is behind the pulse on the pin B. Based on these outcomes, we can determine the direction. Updating the target position. This is just really updating the display. So here, what you can see is that first I put the cursor to the pixel number 60 on the x-axis. I should maybe do this. And then and this is in pixels, and this is tricky because this is in lines. So 60th pixel in the 0 line, I just print a bunch of spaces. So I erase the previous value, and I put back the pixel, the cursor to the 60th pixel, and then I print the target in millimeters using 2 decimals. And once that's done, I don't need to update this value anymore until new value comes up somewhere because I changed something. So I just disable the printing. And then, this is the stationary part. So again, it's very straightforward. I put the cursor somewhere, 10th pixel in the 0 line, and I print this text. And then I move a bit in the screen towards the right edge of the screen, so 60th pixel on the x-axis and still in the 0th line, and I just print this. And here you can see that I have a function which accepts an argument, which is now the target position, which is defined in number of pulses. So this converts the number of pulses to millimeters. And this is good because I promised you that I explain how to convert the number of pulses received from the encoder into millimeters, using the pitch of the lead screw or threaded rod, and the gear ratio, and the number of pulses per revolution from the encoder. So let's jump to this function, and it's a very simple function, as you can see. So it accepts a long variable, which I call pulses, and then here locally we define these pulses in millimeters. So what it does is that, first of all, I want to cast this into float because it will be in millimeters, and it will be with 2 decimals. So I need it to be in float. So what we need to do is we have to divide the number of pulses. So that is the number of pulses created by the encoder. We divide it by the gear ratio defined in the data sheet of your motor. And again, don't mix it up with the RPM value. RPM is just the speed of your main shaft, but the gear ratio is a different stuff. And that can be sometimes confusing on these AliExpress pages. So always check it twice. I mixed it up many times. So here we know that 298 is the gear ratio. And that means that the motor, the shaft of the motor, has to turn 298 times in order to do one full turn on the main shaft, on the threaded shaft. And why we multiply this by 3 is because one turn of the motor shaft creates 3 pulses, because the encoder on it is a 3 pulse per revolution encoder. So that means that if you want to have 1 turn on the shaft, on the threaded shaft, then you will register 3 times 298 pulses. So that's what we have. And that has to be multiplied by the pitch of the thread. And then the pitch of the thread here is 0.7 millimeters. But be careful, because the M4, which is this thread, can be also 0.5 if it's a fine pitched thread. So always double check these things. So then if you multiply basically the number of total pulses, which is this, received by 1 turn of the threaded shaft, you multiply it by the thread pitch, you receive the linear displacement on your main shaft. Then if you have your target position, which is in pulses in millimeter, then you just rearrange this equation, and one side will have the pulses, and then the other side will have the pulses in millimeter and all these parameters. And then you know how to convert your target position into number of pulses. I hope it was clear. So then we have to check the rotary button. So this is a function which we call. So if the switch is 0, remember input pull up, so it is high by default. And here is our debounce. This is not needed. So here we enter this function and we check the time again. So if the time since the last click was more than 1 second, we enter. So that means that if there are multiple pulses coming in within less than 1 second, there is only 1 click registered. So you cannot have bouncing. And then here, this basically means that we pass our target position in millimeter to the target position, which stores the value in number of pulses. So this equation here is the rearranged equation here. And then we enable the motor driver, which I think here is actually not necessary, because it will be enabled otherwise in the code, but now I let it here, and if it needs correction, I will correct it and upload the correct code. And we reset the timer, and then we also set the PID enabled variable to true. So the PID code in the main loop is allowed now to run. So we go to that section. So this code is allowed to run now. So let's see how the calculate PID is going on. I'm not going to explain this again, because you have to check my old video. Link is in the description and also there at the top right corner. And then I explained how this thing works. But I want to explain this tiny part. This I used as a dirty solution. I often found myself struggling because the motor was not stopping. You could see that while I was demonstrating the positioning. The motor was not stopping because the error value was either not 0, or the PWM value was very close to 0, but it was not 0, but it was too low to move the motor to the target position. And here what I did is that sometimes I noticed by printing the variables on the serial terminal that the error was actually 0. So I was at the motor was at the target distance, but still the PWM value got stuck at a very low value, typically less than 10 or less than 5 sometimes. So then I just say that if the error value is 0, then the control signal also has to be 0, which will actually in the other function which drives the motor will set the PWM value to 0. So this is a kind of a cheating, but then yeah, it works. But again, if you know it better, please tell me how to do it, because I want to learn it even better. if it's possible. So feel free to comment. So then we have the other function, which is running the motor, and that is going on here. So based on the sign of the control signal, we determine how to run the motor. And these two are very obvious. If we have a signal which is negative, then the motor direction is negative, and positive, then the motor direction is positive. And if the control signal is 0, then that means that the motor has to stop. And here, PWM value is, first I take the absolute value of it, because I just need the magnitude. I don't need the direction, because that is determined here anyway, and the PWM value can only be positive integer anyway. And I cast it into long. And then that's fine, because sometimes the control signal can be, I don't know, 50,000 something. If I would cast it into int, so integer, it would just bug out, because the integer can take 16,000 something maximum. Long can take more, so it's better to use it. And then here I use a cap. Here, top cap, let's call it like that, because we have an 8-bit PWM, so it doesn't make sense to feed the analog write with something higher than 2 to the 8 power. So let's just cap it. It will not run faster or something, and I haven't tried it, but probably it will cause some issues if I try to feed too high values. And then here is my other cheating, and I did this same kind of cheating in my video where I showed DC motor PWM controlling. Because what I do here is that as I showed it with the linear carriage, with the DC motor, when the PWM value drops below a certain value, the motor ceases, it stops. And it still hasn't reached the target, but it was in the, let's say, approaching phase. So it was very close to the target, let's say 10 steps, so 10 encoder pulses away from the target. But then the PWM value dropped below a critical value, and that stopped the motor, because there was not enough power from the motor's side to drive the gearbox and everything, the whole linear stuff. So what I do here is that if we are still not at the target position, so the error value is not 0, and the PWM value for some reason would drop below 10, I keep it at 10. And you have to play around with this value, because it can depend on your mechanical system. Friction, if you have more friction or less friction, these values will differ. But this is how you, I don't say should, this is how you could overcome this issue. Probably, again, there is a better solution, so please feel free to advise. But this is how I solved it. And then, yeah, based on the motor direction, we set up the pins as we did it with the homing. And then here I also do a bit extra. If the motor has to stop, that means we are at the target position. So I set the PWM value to 0. PID is disabled, so we will not enter this loop anymore. And I print the position, which I showed you in the different camera view, based on the motor encoders. So then the motor encoder value is now converted back based on the parameters of the gearbox and so on. They are converted back into millimeters, and that is printed on the bottom part of the display. And then I write the final PWM value based on these parameters, and that's all. And this goes on and on. So yeah, this was the code. And now I just want to show you the cool demonstration. So for that, I start up the serial plotter. You might hear this noise. Now the motor is just homing. So that's nothing exciting. So it's done. Now I just set up a large target position, 15 millimeters. Look at this. So we have 3 curves here, and once this thing stops, I will explain it. It's a bit pity that I cannot scroll backwards. But what you can see is the red thing here, up here, is the target position in terms of pulses. And then here, this orange line was the motor position, the encoder position. So that's where we were heading. And then this was the control signal. And you could see that the control signal is actually coming from the negative side, and then it is approaching 0. And that is just negative because how the motor direction and everything was set up. So if I would move backwards, so I will set the value smaller than the current value, then I believe that the gray line should come from a positive domain and go towards 0. So now I set the target to 6.65 millimeters, which is smaller than the 15 millimeters, so we should move the other way around. And yes. So you can see that the gray line is coming from the positive, and then it approaches 0. And then we see that also the whole thing was like top down. So we started from high value and we go towards a lower value. So then here the orange line was the encoder position, and then the red line is the target position. And just once again, I go to a higher value, 18.7 millimeters. So again, the control signal will be something negative and it will approach 0. And then you will see that the red line will be above the orange line, and the orange line will approach the red line from the bottom. So you see it goes to it, or towards it. And it stopped. So control signal is 0 because we don't need to run the motor anymore. And then the target position, red, is the same as the position of the motor, which means that we are at the position. And then basically that's all. But I wanted to show you that we can follow this real time, and you see how the thing works. So this was a little bit long explanation, but I think it's quite useful because, yeah, if you use this code and if you use these kind of principles, you can build yourself a very nice positioning system based on DC motors. And once again, sometimes they are better than stepper motors because they can be cheaper, for example, they can be maybe faster, and so on. But here you have to rely on the encoder, and sometimes you have to rely on the let's call it mood of the system, because sometimes it can be messy a little bit, but it works. So once again, visit my website, link is in the description, because I put a lot of resources there, and also I put some extra resources, some extra pictures and so on, so please visit my website. And also don't forget to visit PCBWay.com. You can visit my project page where I have my earlier PCB projects, but also if you are interested in making your own PCB or 3D printed product, then go straight to their website and then check if you find your favorite service or product from PCBWay. So I hope you found this video useful. I hope you learned something, and see you in the next video.